All right, let's dive into something incredible. We're going to talk about the invisible architecture that literally powers our world. We're talking about the fundamental rules of electric charges and the fields they create. This is going to be fun. I mean, think about it for a second. From a bolt of lightning tearing across the sky to the very screen you're looking at right now, it's all governed by this unseen power. And by the end of our chat today, you'll get exactly what that power is and how it all works. So, where does this all begin? Well, the story of this incredible force. It starts with a single, tiny protagonist, the electric charge. Every single interaction, every spark, every circuit, it all starts right here, with this fundamental property of matter. Okay, so to really get how this force builds our entire world, we first need to understand the basic rules. I'm talking about the ground rules that every single electric charge in the universe has to follow. You can think of it as the foundational grammar of physics itself. And the very first rule, it's the engine behind absolutely everything that comes next. And you know what? It's beautifully simple. Like charges repel. They push each other away, while opposites, or unlike charges, attract, pulling closer together. This little dance, this fundamental push and pull, that's the basis for everything. Now, here's where things get really fascinating. You might think electric charge is like water, right? Something that just flows continuously. But nope, it's actually more like money. It comes in these tiny, indivisible packets, kind of like the smallest possible coin in the universe's currency. You can have one of these packets, or two, or a million, but you can never, ever have half a packet. That basic unit is called E, and the total charge, Q, is just a whole number n times that amount. All right, the next rule is, thankfully, super straightforward. If you want to know the total charge of an object, you just do the math. You add up all the positive charges, you subtract all the negative charges, and bingo, there's your answer. The total is just the simple algebraic sum of all the parts. Easy enough, right? And this next one is one of the most fundamental, most unbreakable laws in all of physics. I'm talking about the conservation of charge. In any closed-off system, the total amount of charge is constant. It never changes. You can move it around, you can shuffle it from one object to another, but you can never create it from thin air, and you can never, ever make it disappear. It's a constant of our universe. So we've got the rules down. Charges attract, they repel. But how? I mean, really, how does a charge sitting over here manage to push or pull another charge way over there, especially through empty space? What's going on in between them? Well, the answer has a name, and it's called Coulomb's law. But don't let the name scare you. It really just gives us the precise recipe for this force. And it all boils down to two key things. First, the more charge you have, the stronger the force gets. Makes sense. But second, and this is so important, that force drops off dramatically with distance. It's not a gentle slope. It's like falling off a cliff. If you double the distance, the force gets 4 times weaker. But that still leaves us with this incredible puzzle, right? How does one charge even know the other one is there? There's no string connecting them. It's not magic. There has to be something there, something communicating this force across the void. So, what is it? And the answer is the electric field. It's this invisible, all-pervading thing. Think of it like this. A charge doesn't directly see another charge. Instead, it actually changes the very fabric of space around itself. It creates this area of influence, like an invisible web. That's the electric field. And when another charge wanders into this web, it feels a force. The field is the messenger. And check this out. This graph shows you that steep cliff we were talking about perfectly. See how the field's strength, E, is off the charts when the distance, R, is super small? But as you move away, whoa, it doesn't just dip, it plummets. That's the famous inverse square law in action, a fundamental pattern you see all over the place in physics. So we've got this invisible field all around us. Great, but how do we work with something we can't even see? Well, to solve that problem, physicists came up with a really clever visualization tool to help us actually picture what these fields look like. What they came up with are called electric field lines. Now, these aren't real lines you could go out and touch. They're imaginary, but they are so useful. If you imagine dropping a tiny little positive charge into the field, the path it would follow, that's exactly what a field line shows us. It's a map of the direction of the force at any point in space. Now, these imaginary map lines, they have to follow a few simple rules.
First off, they're always continuous. They never just stop in the middle of nowhere. And that makes sense, right? Because the field itself is everywhere. There aren't any off spots in the space around a charge, so our map can't have any gaps in it either.
Rule number 2, two field lines can never, ever cross. I mean, think about it. If they did, what would that even mean? It would mean that at that one single point, the force is trying to push a charge in two different directions at the exact same time. And that's just not possible, right? A thing can only be pushed one way at any given instant. And finally, these lines have a direction. They have a starting point and an ending point. They always flow out of positive charges and into negative charges. So you can think of positive charges as sources, like little fountains spewing out field lines, and negative charges as drains, where all of the lines end. Okay, so now that we can picture these fields, let's talk about an incredibly powerful shortcut. It's a tool that lets us figure out fields in really complicated setups, and honestly, it almost feels like a magic trick.
But before we get to the trick itself, we need one last piece of the puzzle, a concept called electric flux. The easiest way to think about it is to imagine the field lines are like falling rain, and flux is just asking how much rain is passing through a surface, like your window. The more field lines that poke through that surface, the more flux you have.
And this is where the genius of Gauss's law comes in. It says something that sounds complicated, but is actually mind-blowingly simple. It says that if you draw any imaginary bubble in space, the total number of field lines poking out of that bubble, the total flux, depends only on how much charge you've trapped inside. That's it. Nothing else matters. The charge inside dictates the flux outside.
So, why is this such a game changer? What's the big deal? Well, this one simple idea lets us solve problems that would otherwise be monstrously difficult. It tells us things like the electric field inside a hollow charged ball is always zero. It's a perfect shield. Or that from far away, a charged ball acts as if all its charge is crushed into a single tiny point at its center. It even proves that on any conductor, all the extra charge has to hang out on the surface. These are huge, deep insights, all from one elegant little law. So let's just take a step back for a second. We've gone from the simple idea of charges pushing and pulling all the way to this profound law that shapes the invisible world around us. And you know, these aren't just equations on a blackboard. These are the fundamental rules, the invisible architecture that makes our entire modern world possible, from the tiny chip in your phone to the massive power grid lighting up our cities. We've seen how just a handful of simple, elegant rules build the entire world of electricity and technology. But that leaves us with one last big question. If these rules build our world, what else do they control? And the answer really is everything. From the chemical bonds holding your own body together to the light reaching us from the farthest galaxies, it all comes back to this very same invisible architecture. Absolutely incredible to think about. Thanks for joining me.